Good. All right. So good morning, everyone. My name is Tushar Gohad. I work for Intel Corporation. I'm part of the storage performance development kit team, SPDK, if you guys have heard of it. And I work on NVMe Express and some storage acceleration technologies. So, we're going to talk about some of the work that we've been doing in Openstack, enabling RDMA and NVMe-off-Fabrics. It's kind of the first introduction of the two protocols for enabling higher performance storage behind Openstack. We've been working on this with Mirantis and Mellanox for about a year and a half now, and we wanted to share with you guys the state of the project. So a quick show of hands, how many of you guys are familiar with NVMe Express, NVMe SSDs? Okay, that makes the conversation a bit easier. How about NVMe-off-Fabrics? Okay, so I could use some intro there. All right, so why don't we get started? So when we look at the storage options that are available in typical server systems today, you're basically looking at like on the slowest end that most of today's storage software was designed around was essentially hard drives that used the SRAM, which is your typical CPU caches, and DRAM, which are used for buffers. There used to be a big gap between the hard drives and the DRAM. Over the last decade or so, we saw an advent in the NAND technology, which essentially improved the hard drive performance by 10 to 100x, and gave us a lot better latencies. And then 3D XPoint, which is a brand new form of media that a few companies, including Intel and Micron, introduced last year, which basically takes that latency performance even further. It improves it over NAND by about 100 to 1,000x. Now, what this means is essentially even for your single thread applications, you're actually seeing a lot better performance compared to where you were just last year. Now, if you look at a standard server architecture today, most of the storage is connected via a SAS controller, so HCI bus. But then there's a better option, which is a standard called NVMe Express. NVMe Express was designed in 2011. That was the first time the SNIA basically released the spec. And so SNIA is a Storage Networking Industry Association, and they have a body that works on NVMe Express technology. So this was actually a brand new spec, for attaching higher performance media directly to CPU, like your processors via PCI Express bus. What that does is, it basically allows you to, first of all, it's not constrained by the limitations of SAS or traditional PCI buses, which scale only up to 6 or 12 gigabits a second. This can scale up to as many PCIe lanes you have in a system, so gigabytes a second worth of throughput. And as the PCI Express generations improve, there's no limit to the backend performance. These devices come in like various form factors. I put a picture in here, so if you guys have seen it, you would recognize these devices as NVMe. And the beauty here is that these devices are actually multi-queue devices. So if you have many cores, CPU cores in your system, you can basically take advantage of essentially a queue pair per CPU. So multi-threading, these lend themselves much better to multi-threading or using multiple CPUs as compared to your traditional SAS or SATA devices. So that's NVMe Express. This has been a standard around for, like I said, for 7 years. There are many devices on the market that are coming out now. This technology is still pretty expensive. It's getting better by the day, but dollars per gigabyte is a lot higher today than your SAS or SATA devices. So actually, before I say that, I just want to point out one more thing, which is latency consistency for these devices is actually much superior when you compare it to SATA or SAS devices. Now, again, going back to the cost equation, so again, pretty expensive. So it's desirable that instead of putting these devices into like discrete servers, there's basically a desire to pool these devices. And when you look at, for example, a rack of compute servers, and with the newer cloud disaggregated models, you might have a 2U chassis that holds just these NVMe devices that are exported or that are basically consumed by a bunch of compute servers in the rack. Now, how do we achieve that? How do we how do we basically create an efficient network protocol so that a compute servers can talk to an NVMe pooled device that that basically offers the same performance as a local NVMe. So that's where NVMe-oF-Fabrics as a protocol comes in. So most of you are familiar with iSCSI, which is a traditional storage networking protocol, which is what I have called out on the left. So that's your traditional iSCSI stack. You have compute sitting on the other side of the network, and you're basically transporting your SCSI commands over Ethernet. So complementary to that, in the NVM Express world, you have NVMe-off-Fabrics. So essentially, there is a transport that's basically designed to send NVMe commands over a storage networking fabrics, and that's where NVMe-off-Fabrics comes in. NVMe-off-Fabrics is a relatively newer protocol, probably been around for 4 years or so now. It has been defined mainly for the transports that I've listed here. Like the initial work was all done with InfiniBand and RDMA. There are 2 types of RDMA, and for those that are not familiar with RDMA, it's remote, direct memory access. So it's very similar to your DMA concept with CPUs. It's just that it's over a network fabric. And then there are other traditional options like fiber channel are also supported under the standard. And there is also OmniPath architecture, which is in Intel technology used in high-performance computing. So what NVMe-Fabrics standard does, it defines a common architecture for getting to your NVMe Express devices over an RDMA-capable network or a fast interface. And when you look at the modern cloud deployment models, you usually have a set of compute nodes which are disaggregated from your NVMe storage nodes, and this is done so that you can scale your compute independent of your storage, and that's where these fabric interconnects come in, right? So and you look at any of the modern cloud deployments today, whether open source or otherwise, you'll see this deployment model becoming popular. And Intel is actually working on a new architecture called rack scale design, RST. We in fact have a demo downstairs at the Intel booth, which is in the use of these disaggregated models. Being able to dynamically compose nodes out of your compute and storage resources on the fly, and we have a couple of standards in the works with SNIA called Redfish and Swordfish that allow you to stitch together your resources to, put together like bare metal nodes on the fly using rack level components. It's very interesting architecture, and NVMe-off-Fabrics is a baseline technology that allows you to stitch together the compute and storage pieces. So I'll take a pause there, and so Moshe from Mellanox is going to talk about how one of the transports which we focused on in this work as it relates to OpenStack, which is RDMA. So Moshe.
You have another?
Oh, Actually, you know what?
You have the basic.
I think I'll cover that. I'll come back to that later. So, yeah, go ahead.
Okay, so so the question is, how can we maintain how NVMe-over-Fabrics maintain the performance of NVMe? So as Tushar mentioned before, NVMe is a very lightweighted, efficient interface for storage. And when you move it to NVMe-over-Fabric, you want the network not to be the bottleneck. And for that, you need a very efficient protocol with low latency and high bandwidth. And this is where comes RDMA. So if you look in the legacy iSCSI, we have all the TCP/IP stack. And when we have RDMA, we're actually removing all these stack layers and making performance improvement for the network by bypassing all the TCP/IP. So this is just a reference link in the Mellanox community. So change that. Okay, so what exactly RDMA? So Tushar talked about it. RDMA is a remote direct access memory. It's a transport protocol, basically similar to TCP/UDP. And the main features in it, so from the semantic point of view, it has a send and receive, lacking TCP/IP, but it's also, you can ask for a remote memory region and do a read-write operations. You are doing a kernel bypass. So this allows you to gain low latency with the protocol. And we are doing full hardware offload. So this means that all the message headers and structures done in the NIC itself, so you don't use, you're not even utilizing the CPU compared to the kernel. And also from the secure channel I/O, this is all done in the hardware and not in the kernel, such as in TCP/IP. So basically, we covered all these advantages, right? So it supports InfiniBand, and also we can do RDMA over RACI, which is RDMA over Converged Ethernet, and there is also the IWAP. From the software perspective, the API for that, so in TCP, you have the sockets, and in RDMA, you're using the web software interface. So why is RDMA and NVMe are a perfect fit? So both protocols are asynchronic protocols, and both protocols are queue-based protocols. And because they are sharing the similar design, they're doing this perfect fit, and this is why RDMA was the first transport supported with NVMe-over-Fabrics. So if we would take a look on the NVMe, so NVMe have an admin, submission, and completion queues. And in in RDMA, you have send and receive queues and completion queues. So if we send an NVMe operation, it goes to the submission queue. And then this is encapsulated to the RDMA send queues. On the target side, it goes to the receive queues. Keep in mind, this is all asynchronic, and because both protocols are synchronic, so you can do other stuff as well. There's not anything that is blocking. And then once the operation is done, NVMe will put it on the completion queue, and this will be put on the RDMA completion queues from the target to the initiator. Basically, this explains the flow I just mentioned. Okay, so how is this all related to Mellanox? Mellanox is a networking company. We are leading in the RDMA industry for Ethernet and for InfiniBand. We have an end-to-end solutions from the NICs, cables, and switches. So, and we support 25, 40, 50, 56, and 100 gig. We test all the features with the NVMe-over-Fabric. we are contributing to RDMA and the RDMA and NVMe RDMA, so and very optimized for that kind of protocol. So if you want more information, you can visit the Mellanox booth. So a little bit talking regarding the kernel initiator in NVMe-over-Fabric. So usually the initiator is running on the hypervisor. It's doing the connection to the target side. In our case, it will be in the compute node. The package that we are using is the kernel one, which is the NVMe CLI. This is like the command that actually the Nova compute will run to connect to the target. So you have the RDMA transport, the target IP, the port of the target. Another interesting command that we are using in the implementation is the NVMe list. This is used for when we want to discover the NVMe device. We just do NVMe list before and after we do the connect. And that's when we intersect the list, we know what is the current device that was created. NVMe-over-Fabrics, the target implementation. So it's using the NVMe-T package. It has NVMe-T save commands for creating or deleting new subsystems in the network. Using this, this is an example of JSON configuration. You can see here. So we have the namespaces, the path of the NVMe device, and the NQN name. And we use the NVMe-T restore command for load the existing subsystems. Sorry. So NVMe-over-Fabric in OpenStack. This will be available in the Rocky release. I wrote here, we hope, because most of the patches are in. There is the OS brick patch and the Cinder patches already got merged. We're still waiting for the Nova guys to merge the last one. We already also pushed the Tupelo to allow a simple deployment with Tupelo with NVMe. All the patches got merged. Guys who don't know what is Tupelo, it's just a way to do an Openstack deployment. Currently, this is only RDMA transport, so this will require RDMA NICs. The implementation at the moment supports kernel target and kernel initiator. There is also an SPDK target, which is a user space implementation. Tushar will cover this in the last slide. This is still a work in progress. Also, I want to give some credit for the guys that made this happen. Ivan, which is a co-speaker here, Cinder Core and Horizon PTL, right? From Mirantis, he started the first POC of the SPDK. Magic, I hope I'm pronouncing it correctly, from Intel, is doing the SPDK target. And Hamdi Kaider, also myself from Mellanox, we started working on we did the work on the kernel and initiator and target, and also we pushed the Tupelo deployment.
Yes, thank you, Moshe. So, historically, RDMA support was in Cinder years ago. Even before 2016, we've got RDMA support, but only for ISO target driver, and we didn't have any NVMe support from Cinder perspective. But we started work on NVMe support in Cinder in 2016. We presented some POC during the Barcelona summit. You can find it on my GitHub, but it's not production ready. I hope Intel guys will finish it very, very fast because they did good progress here. So in last year, Mellanox team did incredible works to get NVMe target driver merged in Cinder. So finally we get merged in Rocky release, as said before. So you can try it, work on your environment. You just need to get some Nova patches applied to your resources because it's still not merged. But we really hope that it will be merged in Rocket time series, because Nova team asked Cinder to get it merged first, and then they will be ready to merge it to Nova. And according to SPDK target driver to support NVMe in Cinder, it will be merged a bit later, so you will be able to choose what target driver to use, NVMe kernel driver or SPDK target driver for Cinder. Okay. So, as you may know, Cinder is general block storage service for OpenStack. So it allows you to use any storage you have for any OpenStack deployment, and your user should not know what actually do you use. So it's default scheme how any volume attachment works in Cinder. It's almost the same like iSCSI, but we use NVMe initiator and NVMe target driver on Cinder side. So you can use Horizon or CLI or API to attach volume. From user perspective, it's the same as any other volumes without RDMA, like LVM, SAF, NFS-based storages, or any others. So from Cinder side, you just need to configure your Cinder volume driver. Moshe will say a bit later how you should do it, and everything will work as expected. So workflow is pretty same. Once you need to create volume via some API client like Horizon or OpenStack client CLI, then Cinder will use LVM driver and NVMe target driver to create some volume on your NVMe storage. It will use RDMA transport, which is really fast. And after it, you can attach volumes to your host. So it's the same like current work is for iSCSI or RBD transport. So as I said, Cinder is general block storage service. We released multi-attach feature last cycle in Queens, and we really hope it should work in NVMe with RDMA as well. Moshe will confirm it shortly once he or his team will do setup, and it should work. For now, we've got third-party CIs owned by Mellanox, thank you guys. And we test NVMe target over any Cinder patches, so we can be sure that it works as expected. Okay, thank you. So it's an example of how you should configure Cinder to use it. Moshe? Thank you.
Yeah, thank you. So just to mention, we also have CI testing the NVMe changes in the Cinder and Nova. Forgot to mention that. So here is a basic configuration of the backend in Cinder. So this is an LVM backend. We have one of the things we did is changing all the iSCSI proprietary names. There was a iSCSI protocol, iSCSI IP address. We did it like a generic name for target, and then we added the NVMe part. So we have the NVMe helper as a target, the target protocol, NVMe RDMA, the address, the port. This is like a specific things for NVMe is the port ID and namespace, and the target prefix. So how these configurations looks in Tupelo. Basically, Tupelo, you have the YAML files that you can enable a feature. So if you just add to your deployment command Cinder NVMe-over-Fabrics config, it will enable the feature where you run the Cinder volume. This is the same configuration as you saw last in the previous slides for NVMe. with the NVMe storage target. In the future, we also add the SPDK. One point to keep in mind, you also need to load the RDMA modules and the NVMe modules on the controller, which is where the target is running in Tupelo, but this can be also in the storage node. And on the compute, you need to run the NVMe and NVMe RDMA modules, kernel modules. Sure.
Yeah, so again, another show of hands. How many of you have heard of SPDK? Okay, that's quite a few. So okay, so let me talk a little bit more about it because the word SPDK has come up quite a few times in this talk. So SPDK stands for Storage Performance Development Kit. Those of you that have heard of DPDK, this is sort of those concepts applied to storage. So at the base. At the base of all advent of it, what is SPDK and how it came about? Essentially, the baseline is, historically, like when you look at storage stacks, they have been designed with hard drive sort of media in mind, and this kind of goes back to the first storage evolution slide that I showed. This kind of the reverse representation of that. But as we move from the traditional spinning media to, let's say, a 3D crosspoint media where you can get like 500,000 IOPS, in a single drive, and your I/O latencies drop to sub 10 microseconds. What ends up happening is, compared to your drive or the media latency, your software latency suddenly becomes the dominating factor. So essentially, in the old days, the software was written with one idea in mind, that the storage was the slowest component in the system, and you had to wait, so you had to deploy buffers in between. So software always had to wait for IOs to complete. Now in the 3D crosspoint or even in the NVMe NAND world, right? Software doesn't have to wait as long, and so software is essentially becoming the bottleneck in many systems, right? As opposed to, so storage is becoming the fastest component, compute and network are becoming the bottleneck. And how do you solve this compute efficiency problem? That's why, so that's where we started looking at better software architectures. And that's where SPDK came along, right? So this project officially is 5 years old at this point. So what it offers is it's an open source project hosted at spdk.io. It's a set of user space, lockless, and port mode components, really high performance asynchronous semantics. They're designed to extract maximum performance out of your faster media, that the industry is moving towards. It's open source and it's licensed as BSD license. So it's a much more favorable license than the it's non-restrictive, I would say. Yeah, here are some performance numbers as we have measured for various use cases or benchmarks. For example, in the context of this talk, NVMeoverFabrics target based on SPDK, which is a user space target as opposed to a traditional Linux kernel target. We see about 10x better efficiency per core. For a local NVMe device, using your traditional Linux stack versus an SPDK-based stack, we see about 8x better efficiency. And we also have tried this with RocksDB sort of workloads, where we have seen a pretty significant benefit for your 99th percentile or tail latencies. So in general, the software architecture, if done right, provides the levels of performance as listed here. So SPDK started out being just an NVMe PCIe driver and an NVMe-over-Fabrics target, but today, like you can see, we have in the SPDK community, it's an open source community. It's not just an Intel project. At this point, we have mean, we just had the SPDK Summit 2 weeks ago, and we had about 150 companies participate at this point. So, so the effort is not really to create a complete storage stack, but to provide building blocks, such as user space drivers, storage services, including, let's say something that resembles LVM layer, logical volumes, and a file system or a block device, sort of an abstraction on top of that. And then a few other components, such as your familiar iSCSI target, NVMeoverFabrics target, and the corresponding initiator components. So the blocks in purple are the ones that I've highlighted that are relevant to the OpenStack picture. So essentially, we're stitching these blocks together and integrating those under Cinder and Nova, and to some degree KVM, right, to kind of put together this NVMe Fabric stack that's based on SPDK. So this is actually a test that we ran, based on SPDK and the Linux kernel alternatives. I mean, the IOPS chart kind of looked the same because we were limited by network in this case, because the NVMe backend is so fast that usually your computer network are going to be your bottleneck, right? But what I would like to draw your attention to is these secondary axis numbers, which are number of CPU cores in use. So SPDK can essentially hit the 150 gig line rate. We had 350 gig adapters in there with just 3 cores, 3 CPU cores, whereas with your traditional kernel-based models, it would take you 30 cores to do the same thing. So very, very efficient target implementation, mainly because we don't have any context switches between user space and kernel. It's all pole mode. We have per core connection management. There's no intercore communication that would cause you to lock. So this is a lockless model. That's what gives you this sort of efficiency. So we are actually seeing a lot of the traditional stacks being redone in the use of SPDK. So we thought NVMeoverFabrics, bringing that into OpenStack would be best done with kernel, not just kernel, but also with SPDK. So this is the current implementation. That's actually a pull request still, as Ivan mentioned. This is a high performance alternative, like I said, to the kernel LVM and the NVMeoverFabrics target. The flow is very similar. I mean, when you talk about, let's say, kernel versus SPDK target implementation from a Cinder Nova, from an OpenStack standpoint, your flows will be the same. So this should be a very transparent implementation to the user. So Moshe is actually going to give a demonstration of what, how the NVMeoverFabrics flow works today. But before that, I quickly want to give a refresher on a couple of concepts that Moshe will be talking about. So this is something I actually left on purpose before the demo, because so essentially in the NVMe as well as NVMe-Fabrics world, there are three concepts that are important. There is an NVMe subsystem, which is basically associated with your physical NVMe Express ports, which are PCIe endpoints in the system that contain NVMe controllers and NVMe namespaces. The namespaces are mapped to certain physical media, which is flash or 3D XPoint media. And the controllers are basically and there are many controllers for one namespace or the other way around. So essentially, subsystem is a logical entity that that encompasses all of the NVMe components. And whether it's a drive implementation for a local NVMe Express SSD or an NVMeoverFabrics SSD, you still have the same logical constructs, which are subsystems, namespaces, and controllers. So with this basic idea, so Moshe will demonstrate how how all of this works in the context of OpenStack. So.
Thank you. Yeah. So can you start the demo, please? So pre-recorded demo, so we don't mess it up.
I don't believe you have.
Just a second. Technical issues.
Stop your PowerPoint presentation. You have to stop PowerPoint presentation. Pause the screen.
Yeah. Okay. So. So this is basically, you want to start it? This is the command for doing the Tupelo deployment. You see we're putting the, enabling the features. This is the configuration, how the configuration look like with the currently correct modules. Now we're running the deployment. We're shorting this because this is taking too much time, and then we got to complete. This is the Cinder volume backend configuration. You see the NVMe, the subsystems, everything. Then we boot a Nova instance in Openstack. Okay, VM got created. It's inactive. Then we create the Cinder volume. Okay, it's available. And we attach the volume to the VM that we just created. Now you can see the target side, so with the NVMe TCLI. So basically, the subsystem was created on the target side. And now we do the discovery. This is on the initiator side that it was created, the NVMe device on it. And when you do a dump XML on the VM, you can see that the NVMe device and it's mapped to the. Now we're going into the VM itself in the console, log in to the Cyrus, and we can see that we have this hard disk in the VM. So this is the basic implementation we did with the kernel, initiator, and target, and except everything is working except the Nova patch, like we mentioned. Thank you very much, guys.
Questions? So any questions? Yeah, go ahead.
Yeah, I have a couple of questions.
If you could use the mic real quick. So.
I've got a couple of questions around RAID or RAID-like functionality. So how can you implement redundancy with the storage backend, and also how can you aggregate performance?
So okay, if I understand the question correctly, you're talking about redundancy in the NVMe-off-Fabrics model. So like more like multipathing sort of thing, or. Oh, okay. So if you're talking about just failure domain sense, it's with pooled NVMe, it's going to be usually a rack. It's going to be a failure domain. So you're gonna basically replicate across racks. And with RDMA, there's no, we're not there yet. I would say, there are some challenges with congestion control and so on. But that's I would say that's a little bit outside of the scope of this discussion, because this is basically providing a compute node at the essentially a block device that is an RDMA exported NVMe device, right? And then software, higher layer software on top of that is going to handle the replication. So you could potentially have for persistent storage. So let's just say something like Ceph. With an NVMe-off-Fabrics exported block device, that's where you have a Ceph OSD that's replicating to another OSD, right? Essentially, that could be your solution. But I would say that's a little bit outside of the scope. So.
Oh, I'm sorry, we are out of time. If you have more questions, we can continue outside and answer other questions.
Okay, thank you so much.